You know what most people picture when they think about the space between stars? Nothing. Absolute empty nothing. A vast, cold, dark void where there is simply no stuff whatsoever. And that picture, that beautiful, intuitive, completely satisfying picture, is wrong. It is wrong in the most spectacular and disorienting way that physics has ever produced. And the wrongness of it has very serious consequences for anyone who wants to cross the galaxy. Let me tell you what is actually going on out there. The vacuum, the thing we call empty space, is not a passive, dormant background. It is a churning, frothing, seething activity. Every single point in space, including the space inside this room, inside your body, inside the atoms of your hand, is alive with fluctuating energy. Fields are oscillating. Particles are popping into existence and vanishing in time so short that no instrument could ever catch them in the act. The vacuum is not a place where nothing happens. The vacuum is a place where everything is happening all the time, everywhere, at energies that should frankly terrify any engineer who wants to move a spacecraft through it. Now, how did we figure this out? Because you cannot just look at empty space and see this happening. The answer comes from something very deep in quantum mechanics, a principle that Werner Heisenberg worked out in the late 1920s, and it has a very peculiar implication that most people skip over when they first hear it. Here's the idea. In classical physics, a system at its lowest possible energy state is completely at rest. If you have a pendulum and you drain all the energy out of it, it hangs perfectly still. The position is definite. The momentum is zero. Everything is specified and quiet. But quantum mechanics does not allow this. There is a rule in quantum mechanics that says you cannot simultaneously know the exact position and the exact momentum of anything with perfect precision. The more precisely you nail down one, the more uncertain the other becomes. This is not a measurement problem. This is not about the clumsiness of our instruments. This is a feature of the universe itself. And what this means for a field, say the electromagnetic field, or any of the other fundamental fields that fill all of space, is that the field cannot simply sit at zero. If the field sat at zero, with no vibration, no energy, its value would be exactly specified, and its rate of change would be exactly zero, both simultaneously precise. But the uncertainty principle says that cannot happen. The field must always be fluctuating. It must always be doing something, even at absolute zero temperature. Even in a region of space with no matter anywhere nearby, the fields are restless. They cannot stop. Think of it this way. Imagine you have a spring, a simple harmonic oscillator, the kind of thing a physicist loves because you can solve it exactly. In classical mechanics, you can compress that spring, lock it in place, give it zero energy, and it just sits there forever. In quantum mechanics, you cannot do that. The lowest energy state of that spring, what we call the ground state, still has some energy in it. We call this the zero-point energy. The spring is still jiggling, just a little, even when it has given up everything it can give. The vacuum is an infinite collection of these quantum springs, one for every possible frequency, filling all of space, and every single one of them has this irreducible baseline jiggle. Now here is where it gets strange. When you add up the zero-point energies of all those field modes, every frequency from the lowest to the highest, you get a number. And that number is, mathematically speaking, infinite, which is obviously a problem. Physicists have various ways of dealing with that infinity, cutting it off at some high frequency, renormalizing things, and the result still gives you an enormous energy density sitting in the vacuum. How enormous is a matter of ongoing argument. The straightforward quantum field theory calculation, before you apply any cutoffs, gives numbers that are frankly absurd, somewhere around 10 to the power of 113 joules per cubic meter. For comparison, the entire observable universe, all of its stars, all of its gas, all of its dark matter and radiation, if you took all of it and compressed it into 1 cubic meter, it would have an energy density nowhere near that number. This discrepancy between the theoretical calculation and what we observe is one of the most embarrassing open problems in all of physics. We call it the cosmological constant problem. The vacuum clearly does not have that much energy density. Otherwise, the universe would have blown itself apart instantly or collapsed, depending on how the sign worked out. Something is canceling most of it. We do not know what. This is not a solved problem. This is a place where physics is honestly, genuinely stuck, staring at an answer that is 120 orders of magnitude off from what the universe seems to be doing. But here is the thing: even if almost everything cancels, even if the net energy density is very small, the fluctuations are still real. We know they are real because we can measure their effects. And the most famous measurement is the Casimir effect. In 1948, a Dutch physicist named Hendrik Casimir worked out that if you take two flat, uncharged metal plates and bring them very close together, a force will push them toward each other, not because of any electric charge, not because of any magnetic field, not because there is any ordinary matter between them, just because the vacuum is doing something different in the tiny gap between the plates than it is doing in the open space outside. Here's the picture. In open space, the vacuum fluctuations can have any wavelength. The fields are oscillating at every possible frequency. But between those plates, the fluctuations are constrained. Only certain wavelengths fit in the gap, like only certain notes resonate in a pipe organ. The modes outside the plates are more numerous than the modes inside. So there is slightly more vacuum energy pushing in from outside than there is pushing out from inside. The result is a small but measurable force pulling the plates together. This is not a hypothetical. This has been measured in the laboratory. The Casimir force is real, which means those fluctuations are real. The vacuum is not empty. The vacuum has structure and dynamics, and that structure can push things around. Now, you might say, all right, that is fascinating, but how does a tiny force between laboratory plates stop me from getting to Alpha Centauri? That is a fair question, and the answer takes us somewhere even stranger. As you move faster, as a spacecraft accelerates toward a significant fraction of the speed of light, the vacuum does not look the same to you as it does to someone standing still. This is a consequence of special relativity combined with quantum field theory, and it leads to a prediction called the Unruh effect, worked out by William Unruh in 1976. Here is what it says. An observer who is accelerating through the vacuum does not perceive the vacuum as empty and cold. The accelerating observer perceives the vacuum as filled with a warm gas of thermal radiation. The faster the acceleration, the higher the temperature of that perceived radiation. From the point of view of someone sitting still watching you accelerate, you are moving through empty space. From your own point of view, inside the accelerating rocket, you are being bathed in a glow of particles coming from everywhere around you. This sounds impossible. How can two observers disagree about whether particles exist? But this is actually one of the deepest lessons of quantum field theory. What counts as a particle is not an absolute fact about the universe. It depends on who is asking. The quantum state that one observer calls the vacuum, with no particles in it at all, a different observer in a different state of motion describes as a thermal bath full of radiation. The particle number is observer dependent. Now, the Unruh temperature for an acceleration you could realistically achieve with a rocket is tiny. Ludicrously, almost unmeasurably tiny. To heat the vacuum up to just 1 degree above absolute zero, you would need an acceleration of about 2 times 10 to the 20 meters per second squared. For comparison, the surface gravity of Earth is about 10 meters per second squared. So you would need an acceleration roughly 20 billion times the pull of gravity on Earth just to feel a 1 degree warmth from the vacuum. That is not a civilization-threatening obstacle for interstellar travel. That is an interesting physics fact that barely matters in practice. But here is where the barrier becomes real and serious. When we think about traveling the galaxy, we are not just talking about getting to Alpha Centauri in a few decades. We are talking about crossing 100,000 light years. We are talking about reaching other galaxies, other clusters, the deep structure of the cosmos. And on those scales, the vacuum is doing something else entirely. The universe is expanding. Edwin Hubble noticed in 1929 that distant galaxies are receding from us, and the farther away they are, the faster they are receding. And in 1998, two teams of astronomers, studying the light from distant supernovae, discovered something shocking. The expansion is accelerating. The universe is not just spreading out. It is spreading out faster and faster over time. Something is pushing space itself apart. That something is called dark energy, and the best candidate for it is the cosmological constant, which is a way of saying that the vacuum itself has energy. The vacuum, empty space, carries an energy density that acts like a repulsive gravity on large scales. It pushes things apart rather than pulling them together. And this is not just a mathematical trick. The expansion data, the structure of the cosmic microwave background, the distribution of galaxies across billions of light years, all of it is consistent with a universe where roughly 68% of the total energy content is this vacuum energy sitting quietly in every cubic centimeter of space. And this vacuum energy creates a horizon. As space expands faster and faster, distant regions of the universe are moving away from us at speeds that exceed the speed of light. Not because the matter in those regions is physically traveling faster than light through space, but because space itself is expanding and the total recession velocity adds up to more than light speed when you look far enough. Beyond a certain distance, called the cosmic event horizon, information can never reach us. Light emitted from those regions today will never arrive here, no matter how long you wait, because the space between us and them is expanding too fast for the light to cross. And this horizon is getting closer over time, not in human terms, not in any civilizational terms, but on cosmic timescales. The portion of the universe that is reachable by any civilization anchored to one point in space is shrinking. The galaxies beyond our local group, maybe 50 to 60 galaxies bound together by gravity into a cluster called the local group, those are already effectively out of reach. The expansion will carry them beyond the horizon long before any ship could travel those distances, even a ship traveling at close to the speed of light. So when we say the vacuum of space is boiling, we mean several things all at once. We mean it is seething with zero-point fluctuations at every point. We mean it pushes conductors together with the Casimir force. We mean it appears as thermal radiation to accelerating observers. We mean it carries enough energy density to accelerate the expansion of the entire cosmos. The vacuum is not a passive nothing. It is one of the most physically active entities in the known universe, and the activity of that vacuum sets the limits of what is reachable. The cosmic event horizon is not a wall you can maneuver around. It is not a technology problem. It is a consequence of the fundamental energy of space itself. The vacuum energy is real. It is driving expansion, and expansion creates horizons, and horizons are permanent. There is one more piece of this that I find deeply strange, and it has to do with what happens to a probe moving very fast through the vacuum. We established that fast acceleration heats up the apparent vacuum temperature. But there is also the question of what happens to a high energy particle or a high energy spacecraft moving through a background of cosmic radiation and vacuum fluctuations. At sufficiently high energies, there is a phenomenon called the GZK limit, named after Grison, Zatsepin, and Kuzmin, who calculated in 1966 that cosmic ray protons traveling above a certain energy threshold would interact with the cosmic microwave background radiation, the cold glow of photons left over from the early universe that fills all of space. Those interactions strip energy from the particles and produce other particles. There is a maximum energy above which cosmic rays cannot travel enormous distances without being degraded. The same physics applies to any matter moving at extremely high velocities over galactic distances. The background radiation of the universe, which again is a consequence of the thermal history of the vacuum itself, acts as a kind of friction. The universe is not transparent at all energies. The vacuum has structure that interacts with high energy things passing through it. So put it all together. The vacuum fluctuates, producing zero-point energy in every field at every frequency. The net effect of those fluctuations can exert real forces on real objects, as in the Casimir effect. An accelerating observer perceives the vacuum as thermal, as in the Unruh effect. The vacuum carries an energy density that drives cosmic expansion, as in darkenergy. That expansion creates an event horizon beyond which no signal or spacecraft can ever reach. And background radiation from the thermal history of that vacuum interacts with high energy particles crossing cosmological distances. The galaxy is not simply far away. The galaxy is separated from you by a medium that is physically active, energetically dense, and coupled to the structure of spacetime in ways that create absolute barriers. This is not an engineering problem that a better rocket solves. This is a physics problem rooted in what space actually is. Now, I am not saying this to be discouraging. There is something magnificent about discovering that the thing you thought was nothing is one of the richest and most complex physical entities we have ever tried to understand. Every time we assumed we understood what nothing was, nature surprised us. The vacuum of Newtonian physics was a passive container. Then Maxwell showed it had electric and magnetic fields threading through it. Then Dirac showed those fields were quantized and the vacuum had a ground state. Then Casimir showed that ground state exerted measurable forces. Then Unruh showed that acceleration mixed up what we even meant by the word empty. Then the supernova data showed the vacuum was doing something to the entire geometry of spacetime on the largest scales we can see. Each time we thought we had emptiness figured out, it turned out to be more. There is no reason to think we are done. The vacuum is still hiding things from us. The cosmological constant problem alone tells us we are missing something fundamental about how quantum field theory and gravity fit together. The answer to that missing piece will almost certainly change everything we think we know about space and distance, and what is or is not possible across cosmic scales. But right now, with the physics we have, the honest answer is that the vacuum is not your friend if you want to cross the galaxy. It is not empty. It is not passive. It does not just sit there waiting for you to move through it. It is boiling with activity at every scale from the Planck length up to the radius of the observable universe. And some of that activity has put walls around you that no amount of thrust will ever overcome.